Hello, hopefully everyone can hear me. I am Rajarshi Basu and today we'll be discussing the problems of May cook-off. Okay, so let's start with the first problem, I guess. Um, yeah, so I hope everyone has read all the problems at least once. Uh, for this problem, what we were required to do, we are given a sequence. So we are given a sequence of n numbers and there can be like 100 test cases. Um and then we have to check two things in the sequence. First, if all similar numbers are grouped together. So for example, in the first sequence, all the ones, all the twos, and all the fours are grouped together. That's the first thing that we have to check. So for example, in the second sequence, that is not the case. 4, 3, 4, so all the fours are not together, right? And what is the second thing that we need to check? So every number has some frequency. So let's say in the third example, the frequency of 1 is 1, 7 is 2, 3 is 2, 4 is 3. So we also have to ensure that the frequencies are all distinct for every number. So the third example, it's not valid because 7 has a frequency of 2, 3 has a frequency of 2. So both of them have the same frequency, right? So it's not a valid sequence, hence no. For the second case, all the fours are not grouped together, so again it's a no. And then for the first case, both are true. Frequency of 4 is 1, frequency of 1 is 2, frequency of 2 is 3. So, and all the ones and fours are 2 and twos are grouped together, so we are done, right? So let's just say how we want to implement this. We will only be using standard C++ STL library. Uh, so what we can do is something like, let's say we have a int solve here. Hopefully everyone can see this. I'll just make the font a bit bigger. And let's say we have int n, we take some number, we input the array, and now we can have a set of int. Okay, so let's call this s1. Now we go over all the numbers. So for I comma n basically means for I from 0 to n minus 1. So it's just a hash define that I use. What do we do? So we can like simply check for each of the like two conditions separately. So the first condition will be something like, so you want stuff that is grouped together, right? So let's say your current element is ARR of I, and let's say we skip 0. If I is equal to 0, continue. Okay. Now, if the current element is equal to the previous element, then just move ahead. No need to do anything. If the current element is not equal to the previous element, so and like here I guess we should and if the current element is not equal, then what you want to do is you check if basically if s1 contains that like the current element. So if s1 dot contains error of I, so I think actually how you would implement this is find equal to s1 dot end, right? And if this is true, that means my current element is already in my set. Okay, so set, this denotes the set of all visited, like all elements that we have got till now, right? So if this is true, that means, what does this signify? That means, say our current number was 5, our previous number was something like 3, and we have a 5 somewhere back here, right? So here, let's say there was a 5. Otherwise, it wouldn't have been in S1, correct? So that means all the stuff are not together, right? We are not doing this when the current element is equal to the previous element, because then I mean that's expected, right? But only when the previous element is different we do this check. If it's not, then just break out of everything, right? And so this is how you basically check the first condition, and at the end obviously you will add the current element into the set, correct? You also have to add the first element explicitly, since I exited the loop I mean, I continued the loop when I equal to 0, but yeah, so here you would have done something like insert ARR of I, something like this, right? For the second condition, what you could have done is take a map, int comma int. So this map represents, so let's name this as MP. So this map represents element, that is what is the value of the element, and the frequency of the element, right? So what do we do here? It's really simple, just update, like increase the frequency of the element. After that, how do you check whether all the frequencies are distinct? So a simple way to do it is have another set here S2. Okay, I'll explain what we are doing using this set. Iterate over all the elements of the map, right? And in S2, insert the frequencies. So E dot second. So second was the frequency of the element, right? Second was the frequency of the element. Inserting the frequency. So what is the condition that all the frequencies are distinct? If mp.size is equal to s2.size. That means each entry that you put in, it created a new value, right? So if this is true, then like we succeeded. Oops. And if this is false, then output no. So this is how you can, so actually you can just use only this map and this set and not the previous set. You can combine everything together, but I hopefully everyone got the gist of it, right? So this was the first problem. Almost everyone solved the first problem, I guess. Yeah. So yeah, the exact methods are s1.find, s2, s1.insert, but yeah, I mean, I just said contains just for the sake of it. Which IDE I'm using, it's a Sublime Text. Most people use that. I'll go to probably this problem. So this was, I think, supposed to be the second problem, but somehow the string problem became the second problem. But yeah. So the second problem is you are given a matrix. So let me draw a matrix. So you are given, let's take some example. Let's take the last example only. So it said, so what the problem says is that there are two players, player 1 and player 2. What player 1 does is it goes like this. So it goes from the top left, it scans the row from left to right, then it goes down. So it scans the letters like 1, 2, 3, then it goes down from 3, not to 4 but to 6. Okay, 6, and then it scans from right to left, 5, 4, and then again it goes down by 1, and then it searches left to right. Okay, so in kind of an alternating way. So all the odd rows, it goes from left to right, it goes down, and then for the even, it comes to an even row and it goes from right to left, right? So this will be a sequence generated by the player 1. So player 1 generates this sequence. For player 2, it's almost identical. The only difference is he starts from top right and goes left, then goes down, then goes right, then goes down, then goes left. So whereas the first player was going from left to right in the odd rows, it's going right to left in the odd rows. So how will that sequence be? It will be like 3, 2, 1, 4, 5, 6, 9, 8, 7, right? So what do we have to do? So so I think the notation was the matrix was good if the two sequences generated by player 1 and player 2 were equivalent. So in this case, they are not equivalent, right? But let's say in this kind of a matrix, 1, 2, 3, 2, 2, 2, 2, what would have been the sequences generated? So player 1 would have generated 1, 2, 1, 2, 3, 2, 2, 2, 2. Player 2 would have generated 1 2 1 2 3 2 2 2. So in this case, both the sequences are exactly the same. So this is a good matrix. Okay, this is a bad matrix. So what we have to do, we are given a matrix as input, right? Um, so we are given, like, there are again t-test cases. We are given a matrix as input, and we have to try to rearrange that matrix into a good matrix. Like, we have to report whether we can do so, or whether we can do so or not. Okay. So yeah. So for example, so the test data is given as n comma m. So the first line is n comma m, and the second, and like the next n lines are the matrix. So the first matrix 1 comma 1 is like, okay. So okay, we will go into the examples a bit later. So how do we approach this problem? So think about both the players doing the, like, generating the sequence simultaneously. Okay, so how will that be? So the first player, let's say the first player is at this position, right? And the second player is starting at this position, correct? Now immediately what we can see, that for the sequences to be exactly the same, these two positions must be identical, right? I mean, if the first element is not same, then obviously the sequence won't be equivalent, right? So the top left and the top right positions must be the same, right? Next, okay, let me take a bit bigger matrix. So where the player is at, first player is here, the second player is here. So these two positions must be the same, right? Okay, now after the first point, so this must also be 1 in some sense. Okay, after the first move, the player 1 goes to 2, right? And the player 2 comes to 3. Like, the player 2 goes from right to left, right? So again, these two must be the same, correct? And then the player 2 moves to 3, player 1 moves to 3, and player 2 moves to 2. But we have already said that those two must be the same. So after the player 1 kind of crosses the middle line, we already know that they are the same, right? So it's kind of like a palindromic sequence that we get, right? So the first element must be equal to the last element, the second element must be equal to the second last element, and so on. So every row in our matrix, in our final matrix, should be of the form A, B, C, C, B, A. Something like this, right? Otherwise, the sequence won't be the same. Correct. So, like, it should be clear that even the second rows should be of this form, so something like D, E, F, F, E, D, because like the first player was writing like A, B, C, C, B, A, and then he starts from the right end, right? So D, E, F, and F, E, D, so on. Even for the second player, he starts from left to right. Now this is equivalent as going from left to right. He starts from right to left. This is equivalent as going from left to right, because again, it needs to be a palindrome. And then he goes from left to right in the second row. And for that to be equivalent to the player 1 coming from right to left, again, the second row must also be a palindrome. So essentially, what we can figure out from here is every row needs to be a palindrome. So only thing that we need to check is whether we can rearrange all the given elements in our matrix so that all the rows are palindromes, right? Okay, so how do we ensure that? So first criteria is, so let's make some cases. Okay, if m is odd, okay, so m is the number of columns. Here in this case it's odd, right? If m is odd, no matter what n is, so let's say all the elements that occur in the matrix, let them be 1, 2, 5, 7, Okay, so let these be the elements that are occurring in the matrix. Every one of them must have even frequency. Why? Because if an element is placed here, let's say in the position of A, there must be an equivalent element placed on the right half. So since the thing is symmetrical, like along its rather across its like middle column, I guess, I mean along this line. So since it's symmetrical, everything must have occurrence of 2, right? Like 2, 4, 8, even number of occurrences. If something occurs odd number of times, then there will always be something that is left out, correct? So this is the first point that we should note, that if m is even, every character, rather every element must have even occurrence. Okay. Now, what if the number of columns was odd? So we have some leeway there, right? So let's say it was, sorry, x, y. So in a palindrome, the middle element can be anything, right? The left part and the right part have to be equal. But for the middle element, there is nothing like left and right. I mean, it's the middle element. It can be an odd man out. So if m mod 2 is equal to 1, that means there are odd number of columns, then how many at max, how many odd elements, rather odd, when I say odd element, I mean the frequency of the element is odd. So how many odd elements can be there? Well, let's say there are n rows of the matrix. So n is the number of rows, m is the number of columns. So if there are n rows, then there we can only accommodate at most n such like odd man out values, right? So if, so we have to check here that if count of elements whose frequency is odd is greater than n, then it's not possible, right? We can like accommodate at most n number of such like what to say, odd value in the middle column, right? Apart from that, if anything is in the left side, then it must also be in the right side. So odd entries will not like suffice for this. Okay, so hopefully all this is clear. If okay, so there was another case that, so you might think that, okay, what if count of the number of odd frequency is less than n? So if it's equal to n, then it's simple, right? You place everything that has odd occurrence, you place one of their occurrences in the middle row. Now you have everything that has even occurrence, and you just distribute it in the left half and the right half separately. Now there is one other thing. What if the count is less? So what we do then? So we have something like A2, B2, C2, and then we have to fill something in the middle, right? And then again C2, B2, A2, and let me just copy paste this. Okay, so let's say we have A3, B3, C3, C3, B3, A3, and the middle elements, I don't know what to fill in them with, right? Okay, so what we can do, so now first observe that there will be exactly even number of such middle elements that required to be filled. It's very easy to prove. And what we just do is we have some excess elements, right? I mean, there were n into m elements in the original matrix. Even after we arrange all these like all these into left and right halves, we can like leave out the rest of the middle portions to be filled later, and then we can just take the excess elements and put them in the middle like randomly. It doesn't really matter. The only thing that matters is when you are filling something on the left, you fill something on the right equivalently. So okay, so one thing that it's not really an edge case per se, but I mean, I got a few wrong answers because of this. Note that so your code will be something like so I'll exactly show you where I got the wrong answer. Yeah, so I'll just go over my code a bit. So here FRQ is just the frequency map. I update the map. Odd is basically, so I am storing pairs, right? What are the pairs? Pairs is basically the element and the frequency of the element as it's shown in the map. Okay. Um, yeah. So what we do is for the odd elements, I am taking in the pairs into the vector of odd elements. So VVII, this just means vector of a pair of integers. Okay. Yeah, and even means if the frequency is even, mod 2 is equal to 0, then I'm putting it into even. Hopefully this is better now. Yeah, so if m is mod 2 is equal to 0, then I'll just check whether odd dot size is 0 or not. If it's not 0, then I mean we cannot have odd elements, right? So just print -1. This case is also similar as I told. This is basically I'm filling in the columns one by one using the odd element values, and after putting one occurrence of the odd element in the middle column, I'm just taking it into the even file, right? And then I'm going over the even, like I'm filling over the even values here. Like if I fill something in I comma j, I also filled in I comma m minus j minus 1, right? So if I fill something in left, I fill also in right. Now this thing, this j equal to m by 2, then like if it hits the middle, then go to the next row. Okay. So what the error that I made was I previously placed it at the bottom, and that's why there was a case of when the number of rows is anything, let's say 6, 7, something like that, but the number of columns is 1. So if you place this at the bottom, then your code kind of bugs out. So I just wanted to mention this as a possible bug if someone faces it. So you need to put this on the top, not at the bottom. Yep. So yeah, so I faced like quite a few WAs because of that. Anyway, now let's move on to the third problem, right? Okay, so for this problem, we will be using like, okay, so let me just reiterate the problem. We are given a hidden, like we are given a string of the form s equal to t1 plus t1 plus t2 plus t2, right? And then we have to say whether, yeah, so uh, yeah, so we have to basically say whether s can be represented in that given form t1 plus t1 plus t2 plus t2, or like, and if it can be, do we have to find the string? No. So we just have to tell whether s can be represented in this form. So we are given s, we are not given t1 and t2. So the first thing is like s should be a multiple of what, 4, I think, because so if the length of s is not a multiple of 4, I think we cannot really do this, right? Because like, wait, did I say it correctly? Okay, I don't remember. So I think no. If s is divisible by 2 only, then only I think it's fine. Yeah, sorry, that was my error. Yeah. So now what do we do is, uh, so what is the most brute force way that we can think about asking the problem, rather solving the problem? What is the most brute force way that we can think about it? So we can say that, okay, let's say our string s was something like, let's take the sample input. So s has to be a multiple of 2, I guess, not a multiple of 4. Yeah. So we can say that, okay, let us break the string here. Okay, we have a right half and we have a left half. Now let us check whether the left half can be again broken into 2 equivalent strings, right? And the right half can also be broken into 2 equivalent strings. So if this we can do, right? So this is the most brute force way, right? We break the string into two halves, and then we just check whether the left half, so we now have s equal to left plus right, and we check whether left is of the form t1 plus t1 and whether right is of the form t2 plus t2. Now notice that to check whether left is of this form, we have to exactly split the left string at its middle, right? And then we have to check whether this string is equivalent to this string. Similarly for the right, if we, wherever we split right, we have to exactly check in the middle, and we have to check whether the right, like the two halves are equivalent. Okay, so in a very simple way, what is the most difficult part about this question? It's checking whether two substrings are equivalent, correct? This is a very classical problem. It can be solved using a variety of ways. The way I prefer is using hashing. So I'll just give you a tutorial that is, like, at least I learned it from there, so it's quite nice. Um, yeah, so this is the link to the tutorial. It explains hashing very well. It explains how you can, like, it has several example use cases on hashing. So what do we like get? What is the benefit of hashing? We can check whether two substrings, right, whether two substrings are equivalent or not in constant time. Okay, I'll not go over hashing in details, but refer to the link that I gave. It just checks whether whether two substrings are equivalent or not in constant time. So what is the algorithm after that? It's just find a place to split into L and R, and then split L and R into equal halves, right? And then just check whether, so let's say L, the equal halves where L becomes L1 comma L2 and R becomes R1 comma R2. We just check whether L2, L1 and L2 are equal and whether R1 and R2 are equal. If at any place that we find that L1 is equal to L2 and R1 equal to R2, then we are done, right? So this step, checking whether L1 equal to L2 and R1 equal to R2, this can be done using hashing in order 1. And we have to find a suitable region to split. So we basically try all the places that we could have split. So this loop is order n, right? So you can effectively do everything in order n, and hashing takes a pre-computation time of order n. Okay, so this was the problem. And apart from hashing, I guess you can do it using KMP functions and like basically any string matching thing, anything that you like. Okay, so why does something like, so couldn't we have just said that s dot, say, like L1 dot like equal to L2 and using some substring function and using some compare function, stuff like that? All of those functions work in or like linear time. So if you have k characters, so if you have k characters that you want to check, then substring, equality, compare, everything works in order k time. So effectively it's like a linear time algorithm every time inside the loop as well. So it quickly becomes like order n square, right? I mean, it's not exactly linear time. I mean, it must break somewhere before whenever it sees some different characters. But worst case scenario, it's quadratic time. So yeah. So the best way to solve it is in order 1 time using hashing or something like that. As for collision checks, like risk of collision using hashing, um, a common method to avoid that is using double hashes, but again everything of that sort is mentioned in the blog that I linked. Yeah. So this was again a short and simple problem, I guess. So the next problem is, this is div 1. Yeah. So the next problem we can discuss is this one. So this is kind of like a minimum spanning tree, but it's not quite. So it says that you are given n cities. There is an edge between two cities I and J. Like there's an edge between, let's say there is an edge between every two cities I and J, and the cost of that edge is I and J, where I and J is the and is the bitwise AND operation, and we have to select n minus 1 edges to connect everything, right? So it's kind of like a minimum spanning tree. If you were given the entire graph, then you would have just done a minimum spanning tree algorithm. But unfortunately, n is equal to 10 to the power 9, so no way you can have the graph. Even for n equal to 10 to the power 5, generating the graph is not really feasible because number of edges is quadratic in the number of nodes. So the moment you see 10 to the power 9, that should give you a clue as to what to do. Like you obviously cannot have some generate like something too complex. You cannot have anything that is too complex. You cannot have anything which actually considers nodes, right? Because the number of nodes itself is so high. So there must be some little trick that we are missing, right? So when I first saw the problem, so what observations can we make about this problem? So, right. So what all can we observe about this problem? So first, note that all the cities from 1 to n are given to us, right? So 1, 2, 3, 4, 5, 6, 7, up to let's say 30. Okay. Next, so this is an interesting point. It's not a random set of nodes that are given to us. It's all numbers. Okay. Next, it's a bitwise AND operation, right? So the cost is a bitwise AND operation. Okay. That means that, so okay, so the cost is so that means there must be something involved with bit operations and noticing something about the maybe the lowest common bits of a number, maybe the highest bits of a number, something like that. Okay, so involves something with bits. So some clever observation. Next, another curious thing to note is every odd number. So every odd number. Okay, so can we take any hints from the actual minimum spanning tree algorithm? So in the actual, like let's say CRUSCUL's algorithm, what do? We take the smallest like viable edge present, right? So if we tried to do that right now, like at the beginning of the thing, what do we end up with? We see that it's like we still have this one wala number in our list, right? So we cannot have any edge cost that is less than 1, correct? Because there was some criteria that with positive cost. So the minimum positive cost is 1, correct? We can connect one with many nodes, right? We can in particular we can connect one with any node that is odd, because all those nodes will have the lowest bit set, right? 1 second, just. With one we can link everything that is odd, right? So with one we can link everything that is like 3, 5, 7, 9, 11, and so on. What are the nodes that we have left? We have the even nodes left, right? The nodes with the even what to say, the even labels. For those, for all of the elements that we have left, so let me call this as group of 1. Okay, so for all the elements that we have left, so let's write down their binary representations, because why not? So 2 is 0, 1, 4 is 0, 0, 1, I guess. 5 is 0, 5, not 5, sorry. 6 is 0, 1, 1. Because notice that 3, 5, everything will have the first bit set. So we can just pair them up with 1, right? So all of them were in the group of 1. So 8 is something like 0, 1, 1, 1, and so on. So now, okay, let me just write it for a few more numbers. Okay, did I write 8 correctly? So it's like 101, 12, it's like yeah, hopefully I'm writing the bitwise things correctly. Yeah. So notice that now 2 was not present in the group of 1, right? So we want to, let's say, make a group of 2. So what are all the things? So the thing that I'm trying to say is we cannot have any edge weight of 1 right now, correct? Everything that had edge weight of 1 we already included in this group of 1 thing. Now let's say if we have anything of edge weight 2. Why not? Because we can pair 2 with not 4. 4 does not have the second bit set, but with 6 we can have them set with 10, we can have them set with 14, and so on, right? So 2 we can pair them up with um, like 6, 10, 14, and so on, right? And like you can say that 18, 22, all these will also be there. So group of 2. Okay. So what are we effectively doing when we are doing these simulations? We are matching all the numbers with a specific lowest common bit, right? So in the group of 1, all of them had a lowest common bit, like lowest set bit of 1. For all the numbers that we matched with 2, everyone had a lowest set bit of value 2, right? What do we do next? You might think that, okay, why not with 3? Well, 3, we have already taken the 3 in group of 1, right? I mean, so let's, for sake of it, assume that we had put in an edge from 3 to some other number k, right? That means, and that edge, and the edge weight was 3, right? So that means it would have the first bit set or the second bit set, right? Because the notation of 3 in binary is just 1, 1. So, but if it had the first bit set, then we could have included it in the group of 1. If it had the second bit set, we could have included it in the group of 2. And notice that when I include something in group of 1 or group of 2, my edge weight from that to like my edge weight that is I'm like adding into my minimum spanning tree, its value is also 2 or 1, because we are connecting everything with 1 or 2, not with, we are not connecting stuff with 10. Okay, we are just connecting with 1 or 2 and so on. So 3 is doesn't make sense to make anything with 3. So 4 has a new lowest set bit, right? So 4's lowest set bit is like the third bit is set, right? So for 4, we find all the numbers whose lowest set bit is 3, and we put an edge from 4 to all those numbers, right? So the first number that I can find here is, I guess, 12. So the first number is 12. Then I think you can prove that its next number will be 20, 28, and so on. Hopefully I'm not incorrect here. Yeah, so we will call this the group of 4. So a pattern kind of emerges that even after like the 7, we will be connecting everything with 8, nothing from 5, 6, 7, right? Because if we try to connect and some node k with 5 or 6 or 7, that means their edge weight value will be something higher than we could have achieved using 1, 2, or 4, right? I mean, they either have the first bit set or the second bit set or the third bit set, right? So if it had, let's say, the second bit set, we could have just connected it with 2, correct? So why bother using an edge weight of, let's say, 6 when we can connect with edge weight of 2? So uh, so yeah, so we will only consider like new nodes to connect stuff with when it has a new lowest set bit. Okay, and again, we don't want anything that is high, that has like more set bits, right? I mean, we don't want 11. Like you might say that, okay, let's say 8 with 11. So 11 also has a lowest set bit of, okay, no, 11 does not have a lowest. I mean, 11 also has the third, fourth bit set, right? So 11 also has the 4th bit set. But thing is, we can, so whatever we connected with 11, so if we connected 11 with K, we could have connected either 1 with K or 2 with K or 4 with K, right? One of the bits would have been common because, yeah, I mean, yeah, okay, so hopefully the intuition is clear. So what we just do, we make groups according to the lowest common bit, so like 8, 16 and so on, and up till whatever is the maximum like power of 2 that we have in our set. Okay, so in this case we took till 30, so 16 is basically the highest power that we want to go till, and we can say that every other number will get matched to at least one of them using their lowest set bit, right? Okay, so what is the cost of this minimum spanning tree? And like, so we have two things remaining. First, these groups are connected. Okay, so this is one connected component, group of 1. The group of 2 is another connected component, but till now we haven't placed any edge between a node of group 1 and a node of group 2, or a node of group 2 with a node of group 4, and so on. So all these are kind of distinct connected components at the moment. So till now, what is the edge cost? Well, you just need to count the number of values in the group, right? So here, for example, we have till 22, and then I guess 26 is also here. So I mean, how am I saying that 26 is here? Well, it's just like there's a pattern like 4, 4, 4, right? So since the lowest set bit that you can have is 4, every time you update, you are kind of adding 4 into it. I mean, uh, in some sense, like the lowest set bit has to be 2, so you have to add something of the sort of 4 and so on. So that's why you can say that, okay, 26 will be here. And similarly here, 4 plus 8 is 12, 12 plus 8 is 20, 20 plus 8 is 28, and so on. So you can count the number of values in a group very easily using some simple formula. For the formula, just refer to the editorial. I guess it will be, the editorial has been released, right? Yeah, so the editorial has been released. It will be there. Just check it up. And then what is the edge cost in each group? See, in the group of 4, every edge is of cost 4, right? Because we are connecting 4 with 12, 4 with 20, 4 with 28. 4 is the minimum value, so you will have an edge cost of 4. Similarly, in the group of 2, you will have, every edge will have a cost of 2, and so on. So you can find the cost of all the edge connections till now. Now, how do we add edges between two groups? Well, so what we do is, let me just write down this numbers a bit, right? So it's 1, 2, 0, 1, so on. So, okay, so the idea is something along that the next item in every group will have will have the lowest set bit to something that is like, okay, let me just clarify a bit. So in the group of 1, after 1, the next number that we have after 1, that will have a bit of like the next bit set, right? I mean, 3 is a number after 1 and it has the second bit set, correct? What we do is we connect 2 with 3. Okay, similarly we connect 4 with 5. Okay, not with 5, I think. So we connected with 5. So we connect 2 with 3. We connect 4 with 6, I guess. I mean, 5 or 6, I mean, doesn't really matter. So you connect 1 with, you connect 2 with 3, you connect 4 with 5, you connect 8 with 9, and so on, right? So you connect 8 with 9, you connect 16 with 17. So all these numbers, so if we have, so the group of, so group of K, where K is equal to sum 2 to the power I, we connect. So the group of k will have everything which has lowest set bit of k, right? So connect k. So connect k with k plus 1. Why? K plus 1 is in the group of 1. This is guaranteed, right? For any k of this form 2 to the power I, k plus 1 has the first bit set always. So k plus 1 is in the group of 1. So once you connect everything, like every such k to k plus 1, that means in effect every group is connected to the node 1, right? And what is the cost? The cost is just 2 to the power k, right? So this is how you connect the all the groups together. Okay. Now there is just one catch in this, and again all the costs you can just run a loop, or you can even find out using some formula. I think it will be something like 2 to the power 1 plus log base 2 of base 2 of n, and like minus 2 or something, minus 1, something like this. So you can just figure out a formula. Again, it's given in the editorial. There's just one snag here. That's what if 1 to n we had n equal to 2 to the power I. That means there will be a group of n, right? So there will be a group of n itself where there will be no n plus 1. So you cannot really connect that group with anything above, right? Because for n, so if n equal to 2 to the power j, the lowest set bit is 2 to the power j, like is j. All the previous elements before n, you did not have anything that was like any bit set at j, and even after n you don't have anything so that you could connect n with say n plus 5, and then that n plus 5 would have been connected to something below. So in that case you cannot really connect the whole graph. So that was the only edge case, I guess. So yeah, so this was the full problem, I guess. Like any doubts, anything, feel free to ask. Okay, so let's I guess move on to the next problem. Okay, so the third problem in div 1, I guess. So the second problem in div 1 was that this string problem. The third problem is based on trees. Okay, so it basically says that you are given a tree, and I think I have drawn nice tree. Okay, let me draw a nice tree. And there is some parent. So I'm just drawing kind of one structure of the tree, right? These are the edges. I mean, there are other childs and other parents and stuff as well. So I'm just drawing what pertains to one single query. And let's say this node is X, this node is Y, right? And we have to check whether the path satisfies this condition that there is some node here somewhere P. So let me give some values here as well. So let's say this is 3. Let's say this is 5. Let's say this is 11. This is 8. So every node has a given value. So these are not the node labels. These are the AI values that were given. Okay. 7, 5. So we have to say whether there is a path like this where there is a certain node P, okay, so that X to P everything increases, and Y to P also. So you move around the LC and come here. Y to P also everything is strictly increasing. So note that the condition says it needs to be strictly increasing, not equal to things are bad, right? So we just have to find whether such a path exists or not. So I'll be using a few notations here like lowest common ancestors, sparse tables. If you don't know what those are, I'll give you some links. Hopefully these should help. I mean, these are very common topics, so yeah, hopefully these links will suffice. Yeah. So we have to check whether such a path exists or not. And the problem might be, so what if let's solve a simpler case of the problem, right? What if we were told that this P node, instead of it being anywhere on the path, it has to be exactly at the LCA. So what would we have done then? If we could have checked whether the path from X to LCA was increasing or not, and similarly for Y, if the path from Y to LCA was increasing, if both of them were strictly increasing, then it's a yes, right? Now in this scenario, we cannot afford to go up till the LCA, right? So what we should think is, like go up till it is increasing. So in this case we can go up till 11, and then we know that the rest of the thing from the node P to LCA must be decreasing, right? So I'll just draw one more node. Rather, I do this. And I'll name this as, let's say this is 9, this is 8. So we can like kind of in our mind, and this we are not, till now we are not doing in programmatically. What we know, what is a kind of the structure that we are looking for, right? We are looking for something that is increasing till some point P, okay, then decreasing from point P to the LCA, okay, and in the other half, so we can, like without loss of generalization, we can just assume that the P thing will lie on the path from X to LCA, okay. It's kind of similar to how you will do it when it's the opposite case, when it lies from Y to LCA. And for the rest, when like this you have, and then we also have to check whether the path from Y to LCA is strictly increasing or not, right? So we have kind of deduced our entire problem into two things. If we can check whether a path from some node to some ancestor, okay, so what are the key things here involved? So one, support checking whether a path from some node X to some ancestor Y is increasing or not, increasing or decreasing, okay. If we can somehow answer these queries, whether the path from X to some ancestor Y is increasing or decreasing, then we can effectively solve the entire problem, right? We can just find the first, yeah. So what is a brute force way if we could, let's say, answer this query easily? So what does yeah, so what is the brute force way? We could have said that, okay, let's fix a certain P here. Let's say this, exactly this index must be P. Then we check whether X to P is increasing or not. Then we check whether P to LCA is decreasing or not, and we check whether Y to LCA is increasing or not, right? Using just three simple queries, and we had assumed that we can answer these queries fast. Using just three simple queries, we could have answered everything, like we could have solved the problem, right? Now, the only bad thing here is we had been fixing this point P, correct? But notice something, if we said that this point was P, how were we checking whether X to P is increasing or not? I mean, we had some valid, like we had some magic function here, right? But we, like, how can we, so what do I mean is, how can we kind of simplify the approach to ensure that any random node P, we don't select any random node P, okay? So what we do is, for every node, so for every node X, and I mean, not just X, for the node with value 11, with the node with value 9, for everything, we store the, like the lowest ancestor, and this is not the lowest common ancestor, this is just the lowest ancestor, which had a where the sequence kind of became from increasing to non-increasing, okay? So what do I mean by that? For X, the lowest place, the lowest ancestor where till which from X to that point is increasing is 11, right? So something like this. So for X, we store that, okay, till 11 I have increasing. For 5 we store that, okay, till 11 we have increasing. For 11, this kind of doesn't make sense, right? Because just above it there is a decreasing type node, right? So doesn't really make sense. Similarly for 9, it doesn't, like the query itself doesn't make sense, and you can like kind of think of it that for these two nodes, actually this is, I guess, a better way of looking at it. The lowest ancestor till which it was increasing is 11 itself, right? So for 9 it's 9 itself, for 8 it's 8 itself, for all these values 7, 5, 3, everything, the answer is 8, right? And okay, so one thing you might assume that, okay, why not something that was above 8 as well? So yeah, I mean 8 or something even above 8. So how does this kind of simplify our choices for P? Okay, so the main problem was we were finding it hard to really look at all the P's, right? I mean, that is really too much of a brute force. So how does this help us simplify? So let's say we are starting at X, we are standing at X right now. Let's look at the first vertex. Rather, we have this till what point we were increasing, right? We have this already stored using some pre-computation. Okay, we will not go over what pre-computation exactly right now, but let's say we have this stored. So I know that if as I climb along the parents till the position 11, I will have everything that is strictly increasing. Okay, so all well and good. Now it is imperative that the point that we get here, so let's say 11, this must exactly be P. There can be no other choices for P, right? So from the problem statement, if we try to see how, I mean, it has to be increasing, right? I mean, there cannot be any other values of possible values of P, let's say here, because if both were true, that means this entire portion was increasing. But again, we have a contradiction here itself. So it's kind of easy and intuitive to see that there will be exactly one choice of P that is valid. Okay. Whenever I say that, okay, go up till 11 and I see that 11 is here, I know that this must be our P value. So notice how we fixed the value of P directly. Instead of trying all the values, I instantly know that what is the plausible value of P. Now, what if we were, so let's say 8 was connected to, so the ancestor of 8 was something like 11, 12, okay, here. And since we don't know whether which is X, which is Y, obviously, when we are given the problem, let's say we had done the same thing from Y. For Y, the highest point is 12, right? Now, we know that the LCA of X and Y is 8. We again saw that the ancestor chain that goes from Y, it increases up to some ancestor of even the LCA. So there is no possible places for P in this stretch, correct? That means P cannot be here, okay? So again, we know that P cannot be here, that means P must be here, right? So once we determine the value of P, our job becomes much easier, right? So we know that this portion is already increasing. I mean, since that is P, we got the value of P on that criterion only, right? That this part was not increasing. Where was the first time that it did not increase? Okay. And for this portion also, we know that everything is increasing if the the lowest ancestor of y that had that break point of increasing thing, if that is higher than the LCA, then we know that y till LCA is everything is increasing. The only problem here is how do we check whether this portion from P to LCA that is decreasing or not. But see, increasing and decreasing, it's very similar, right? I mean, if you can somehow calculate the data for increasing, it's very easy to calculate the same data for decreasing also. I mean, it's entirely equivalent. So point is, once you reach P, you use identify what your P of the sequence is. You just check whether the lowest ancestor where till which the value decreases from P is higher than or at least LCA or not. I mean, if it was between this P position and LCA position, that means you would have kind of decreased till some point here, and then you would have again increased from this black node to the LCA, right, which is not valid. So we want everything to decrease. How do we check? We check whether the lowest ancestor till which point it was decreasing is higher than LCA or not. I mean, when I say higher, I mean it can also be the LCA itself, okay? Because LCA is it's valid. Yeah. So that is how, if you can answer this query, rather if you can find these values till what point in till what is the lowest ancestor till which my ancestral chain kind of increases and decreases, like we have to store both the values, we can easily answer the queries whether the path is of the given form or not. How do we compute these values? It's just a simple DFS, right? So let me just show the DFS. I'll just check if there's any comments in the chat. Okay, someone asked, can't we do double DFS and offline querying? I don't exactly know what you mean by that, by double DFS. Queries can be offline, online. Queries are online only. It doesn't really matter. So yeah, so the DFS will be something like, I mean, it's pretty simple, right? You just have a DF, so void DFS. You can store two values. So I usually code DFS like this. So first you store the depth of the node equal to depth of, so P is the parent node is the current node. So I'll just change the rotation a bit. P plus 1, and I am assuming that cur is not the root node because then it will have no parent, obviously. And then we also have some best increasing, something like this, which effectively stores the value that we are trying to compute, right? What is till what point is my sequence increasing as I go along my ancestors. So best increasing of current. So let's say if ARR, so ARR is the, or rather let's say the val of cur was greater than P. So my value is greater than P, that means my decreasing chain, best decreasing of cur equal to best decreasing of P. And if val cur is less than P, that means my value is lesser than the parents, then we will have something like best increasing of cur is equal to best increasing of P, right? I mean, whatever the lowest ancestor of my parent was, I also have the same thing, right? Because from my parent also it was decreasing. sorry, it was increasing from my current node to my parent. This part is also increasing. So whatever the value of the parent node was, it's the same value. I hope the intuition is clear for this. And when do we set a new value? So here we also said that best increasing of cur is equal to cur, right? Because if the value is if the value decreased, then the increasing sequence kind of like broke off, I guess the correct grammar. And similarly for here, we will set the value of best decreasing of cur to cur. And this is how we kind of generate the values of increasing and decreasing things using using this DFS. You can see from the setters code, etc. Yeah. So one thing that was, I think, a bit not mentioned in the problem, notice that everything has to be strictly increasing, right? So everything is strictly increasing. So what about when there are equal values? I think there were a few comments as well. What if there were equal values? So for equal values, this sequence is not true. So if there are two values that are equal in your like sequence of nodes, then it's not a valid sequence. So there are two possible ways that you can handle it. You can put a equal to sign here, I guess, and some other details are necessary, I think. But yeah, so you can either do this, or the way I prefer is you just explicitly store which all nodes and their parent nodes have the same value. That way, when you are given an x and y, you can just query if there is anything that is of the same value directly. I mean, that way it's a bit of a less trouble, right? So you can just do something like node has a value, node has a value of, let's say, -1. If the node has a value of -1, if val of node equal to val of node is equal to val of parent of node, and then again you can store that lowest ancestor with value -1. So this value is not equal to the given value. This is just some extra values that I'm defining. And if that lowest value was, the depth was greater than LCA, that means it belongs to one of your paths. Then you can just report that it's not possible. But I think you can do some equal to, less than equal to, greater than equal to as well. I'll just link a submission that I saw using that equal to thing, no extra checkings. So yes, you can see this submission. Yeah. So this just handles everything in the equality case in of itself. So that's better, I guess. Anyhow, so this was the, I guess, the third problem of div 1. Yeah. So for the fourth problem, just give me one. So this problem was about inversions, and so I'll just give the brief of the statement. What the problem essentially wanted was, we are given a subarray, right? And then you have to count. So rather, you are given an array, not a subarray. So you are given an array. For all subarrays, define count as the number of inversions in the subarray, right? So this is the standard definition of inversion. Inversion is defined as if I greater than j and ai less than aj. So this is how inversion it's defined, and it's effectively the strength of the squad, right? So let's say this is a strength. So what does it want? It wants us to list all the strengths of all possible subarrays and then find the median strength. Okay. So the length of the array is 10 to the power 5, so it's a huge array. So the first thing that is obviously clear is we cannot really compute all the strength of the different subarrays, right? I mean, that's just not possible. So now the question is, how do we go on finding the median, right? So what we will do is, so one thing is clear, that the total number of subarrays is fixed, right? So we know that the total number of subarrays is n choose 2. So we have to find the median somehow. So what is the way that we approach these kinds of problems where it's very hard to enumerate everything, and it's equally hard to kind of directly move towards finding the best possible subarray, right? I mean the median subarray. So it's not really clear how you will try to uh, tell just by looking at a subarray whether it's median or not. I mean whether its strength is the median or not. So in these scenarios, what we can do is note that we can do something like we can binary search on the answer. Okay. So how do I get the intuition that we want to binary search on the answer for this problem? Again, it's mostly because we cannot directly kind of, like, given a subarray, we cannot really tell if it's a median or not. We don't know what all subarrays have value lesser than it, what all subarrays have value greater than it. It's very hard to tell. So let's look at if we can somehow, so if we can binary search the answer. So step 1 is, let's say, bin search the median value. And what do we do in search problems? We essentially want to check whether that median value is plausible or not, right? Whether it is the correct median value or not. So how do we check it in this case? Well, like the only possible way that you can check it is if there are at least k, like if there are at least let's say the total number of subarrays was capital M. I want to check if there are exactly m by 2 subarrays that is lesser than my whose strength values are lesser than me, right? Now what one thing is common in many problems of this sort is it's very hard to exactly know what is the inversion count of a subarray, but it's easier to know, rather it's not very hard to know what is the exact count, but it is hard to count how many subarrays have some exact count and those sorts of things. What is much easier to find usually in problems is, given a value, is how many subarrays have inversion count at least till this value, right? So exact equality is a hard operation to do. Some greater than, some lesser than things, those are usually easier to find. How many subarrays have a value greater than me, how many subarrays have a value lesser than me. These things are easier to find rather than how many subarrays have value exactly as this, right? So let's see if we can check whether the how many subarrays have, like, so checking basically means if we have greater than, if we have exactly equal to m by 2 or not. What I also want to do is I want to have a function f which returns, so it returns an int value. So it returns some integer and it's given some value. It returns number of subarrays with value less than, rather with inversion count less than the given value, right? So if we can somehow implement this function efficiently, and I'll not going to like right now I'll not go into what is exactly what I mean by efficiently, but it's something like in a linear scan of the array, or maybe n log n or n log square n, like not too high a constant factor and not too high a complexity. Then what we can do inside the check is just say that the return f of value uh, oops, equal to m by 2 or not, right? If it's m by 2, then we are done. If it's not, well, then do some other checking, right? So why is this thing binary searchable? I mean, obviously, if you choose a median value, like your assumed median value is very less, then f of that value will also be less. If it's greater, then it will also be greater, and then you want to find exactly the median value where it's exactly equal to m by 2, right? So the main part of the problem was how do we implement this f function, right? And we want to check how many subarrays exist with a median value, like with inversion counts, sorry, with inversion counts lesser than some given value v, let's say v, right? So actually what we will do is maybe, okay, okay, doesn't matter. So less than v. So again, whenever we have anything to do with subarrays, whenever we are trying to count subarrays, it's always a good idea. Like the first thing that you should think about is fixing a right index and seeing how many left indexes are valid. I mean, it's always a good thing to do. That is the first thing that at least I think about whenever I see a subarray related problem. I mean, counting subarrays. So let's say we have fixed our right endpoint to be here. And so what is the key observation here is we have to count the number of subarrays like this, right? So I'll color code every subarray with a different color, I guess. So so we have to count the number of such subarrays, like you get the point, I guess, which have an inversion, total inversion count of less than v. Now, one thing, like the main thing here is if there is an inversion pair. So what do I mean by inversion pair? This is our inversion pair, right? I greater than j, ai less than aj. If we have a certain inversion pair, let's say like this. Now, when you kind of extend your left endpoint, so when you this is, let's say, your left endpoint, and when you move this left endpoint towards the left, right, you have already fixed a right endpoint at the red value. When you move this, so what about that? Okay, what color is that? I guess turquoise. What about that greenish turquoise inversion pair that we were looking at? Till now, it's not included in our subarray. Still not included. Still not included. Now it is included in our subarray, right? Once it is included, it will not go out of our subarray. So once this pair contributes, it, like, we can extend the left index however much we want. In all our subarrays, this inversion pair will always be there, correct? So what do we gather from here? The number of inversions as we go from, like, as we sweep this line from left to right, it always increases, correct? So let's say we have a magic data structure which can calculate the value, like the inversion count of a subarray very fast, okay? Now we say that there will be some value here. So let's say a certain, let's say this index. So at this index, the subarray, like the inversion count, is greater than v. Now, since all the inversion pairs that contributed to this v value, they are not going away as I move my left index from here onwards to left. That means everything that is to the left will have a greater, like have an inversion value of greater than v, correct? Okay. So that means all the subarrays which have a inversion count less than v lie in this zone. So they lie in this zone, and everything that is greater than v lies to the left of this zone, right? So they are ineffectively, they are contiguous. Now, what is another observation that we can make? So we fix the right endpoint to be this red line, correct? Now what happens when we move the right endpoint one place? Now again, the same observation. If an inversion pair something like this was already formed, when we move the right endpoint once, and let's say if the left endpoint was fixed, then that inversion pair will always stay there, correct? So let's say for this right endpoint, let's say for this right endpoint that we had chosen, and let's say for some left endpoint here, we had certain inversion pairs. Let's say some inversion pairs like these are all inversion pairs. Let's say when we move the right index one place here, okay, so when we move the right thing, here, okay, these for that particular left index, for that particular left arrow left index, yellow arrow left index, these black inversion pairs still remain, right? So the main point here that I'm trying to make is this cutoff value, right? This cutoff zone that we have said, that where it was the first time where the inversion count was greater than V. The inversion count, even after we shifted the right endpoint by 1, it will not go left. So the cutoff zone won't go left, right? Because whatever inversion pairs was there in this region, it still is there. Like, to be honest, it has probably increased even more, right? So that means that in actuality it will either stay here or it will actually move right, correct? So this kind of tells you that, okay, so that means as I shift my right endpoint, my left cutoff index, right, the first index where the inversion count is greater than V, that will also shift towards the right, because all inversion pairs that were once inserted, they are not removed. So hence, if we like, this kind of leads to a two-pointer algorithm, right? So what do we do effectively? For every right index, we find the cutoff left index, and every sub-array. So what is the total number of sub-array that is contributed by that right index? So if cutoff left index was, let's say, L, and right index was R, it's just R minus L, correct? So there are R minus L sub-arrays in between, all of which have their right index as the red line, and all of whose left indexes are like greater than this sweep line thing that I am holding with my cursor, right? So that's the intuition. Now, what is the key thing that I've skipped over till now? As I said, there was a magic data structure that quickly calculated all the inversion counts. How do we do the magic data structure like that? Well, data structures are usually segment trees. So here also we will also use a segment tree. So what will that segment tree hold? It's just a segment tree on the frequency array. Now, there are two things happening here, right? So how do we kind of update our answer for the inversion count? When I move the right index, I effectively insert this element into the segment tree, and then I query. So let me get another thing. Everything that is between the left index and the right index, all the values, these are kind of my active values, okay? So these values are active values. Okay. So these are the only values that are present in my segment tree, right? So something like, oops. So if J is an active index, meaning, so this means that L less than equal to J less than equal to R. That means in my segment tree, the position of ARR of J was, I had done a plus plus there. I mean, it is accounted for. Okay. So position means, remember that it was our segment tree was built on a frequency table. That's why I'm saying position of ARR of J. I mean, it's basically the frequency of ARR of J, if you want to think about it like that. Right. Now, when I insert a new value, when I say that, okay, this value is now also active, I am effectively just putting it into the segment tree. And let's say the value was X. Okay, so X is the new active value. How do I update my inversion count? So inversion count, this is just number. So this is just kind of sectree dot sum. And what do we sum? 1 to X minus 1. Does this make sense? Because the segment tree was a frequency table, right? So I am inserting something at the Xth frequency. Okay, so sorry, I think I miswrote it. This should be actually X plus 1 up till Maxwell, right? Because all the active values before me were to the left of me. That means if those values are greater than me, that means we have an inversion pair, else not. So among all the active values that were present, how many values had, like how many values were greater than me, that is effectively given by sum from X plus 1 to Maxwell in a segment tree built on a frequency table, correct? This is very standard applications of segment tree. So we just query that portion. Okay, so when I insert this value X plus 1 to Maxwell, how many values are there? Those are the values with which X creates an inversion pair, and you just increment inversion count with that. Similarly, now that inversion count has incremented, you want to check whether my left endpoint should actually go towards right a bit more, right? I mean, it could have gone right once, twice. I mean, you effectively do it in a while loop. It can go right till the point where the next position has inversion count less than V. So what do? You are basically making an element not active anymore, correct? So for that, again, it's very similar. When you are making it not active, you just want to remove how many inversion pairs were contributed by that element with the other active values, right? So you just subtract from inversion count some segmentary sum from 1 to x minus 1. So for the value that you put out, that let's say that is y, I guess you do minus equals sec3 dot sum 1 to x minus 1. I guess this is correct. Yeah, because all the active values now are to the right of me. So there will be an inversion pair if the value that was right of me was lesser than me. That would have contributed to an inversion pair. So I subtract all such inversion pairs. And then, by the way, don't forget to like, what to say. So here we also do a sectree dot update. So at the jth position, I do +1. And here at the, let's say we had removed from the ith position, then sectree dot update I comma -1, something like this, right? And this is the way you kind of maintain your segment tree. And the total number of inversions is just the value of the segment tree at the root. Like the root node of the segment tree is effectively the total number of inversions. Sorry, sorry, what am I saying? Segment tree values are just the frequency. Sorry. Inversion count we are explicitly maintaining in a variable, right? My bad. Yeah, so inversion counts we were explicitly maintaining in a variable. Yeah, so that's how you kind of maintain the inversion count as you do the 2-pointer. And what is the total complexity? Well, in the 2-pointer, you effectively add an element once and remove an element once. Every time you add and remove, you do a segment tree query. So it's effectively n log n, right? So you can do each check in n log n time, and then you have this binary search over the whole thing, right? So this is how you're calculating f of value. You have some binary search as well. So it's overall the complexity becomes n log square n. Hope that's clear. So the last problem we will not be discussing today. Right, so sorry, this is the last problem. So chef and curious queries. So we will not be discussing this today, and I'll refrain from giving any hints. The editorial should be out soon enough, I guess. Yeah, we'll probably have another session for this last problem. Any doubts regarding the segment 3, the last problem that I discussed, the binary search part, anything else? Okay, I guess not. Then yeah, that's it for this session.